Here's a situation which we'll use to assist our meditation on thin film interference. The situation involves white light in air incident on a thin layer of oil, and we're given the index of refraction of the oil as n equals 1.50. And the oil is resting on top of a layer of water, index of refraction 1.33. And we're told that the thickness of the oil film is 1/4 of the wavelength of red light in oil. The task for us is to figure out what we might observe as a result of thin film interference in this situation. As you meditate, think about the impact of the oil's index of refraction on this situation. Note that it's higher than the index of refraction of air, and it's also higher than the index of refraction of the water beneath it. And then, as you meditate further, think about why it's so important that we're told that the oil has a thickness of 1/4 of the wavelength of red light. I think it's a good idea to pause the video here, maybe check the text, do some thinking before you continue on to my analysis. So the first thing we need to know is that the light will undergo a 180-degree phase change when it reflects off of the oil. This is because the oil has a higher index than the air. So as the caption notes, this is equivalent to shifting the whole wave by half of a wavelength. Then we need to think about the oil-water boundary. Since the index of refraction of the water, 1.33, is less than that of the oil at 1.50, no phase change occurs when the light reflects off the oil-water boundary. So, therefore, the difference between the two reflected rays, due to the indices of refraction alone, is 1/2 of a wavelength. The third thing we need to consider is the path length difference between the two reflected waves. The first of these waves is the one that hits the medium boundary at A and reflects off through point D. Then there's a second reflected wave. This one is refracted through medium that has N2, and it travels from A to B to C and out again into the air. So if the length of ABC is some certain number of wavelengths different than the first reflected wave, then the two reflected waves can interfere with each other either constructively or destructively, and this influences what we see. Another thing we have to think about is the wavelength of the light inside the film. In this case, it's an oil film. We defined the index of refraction n as the ratio between the speed of light in a vacuum, that's c, divided by the speed of light in the medium, v. Since the velocity of light is equivalent to its frequency times its wavelength, then we can rewrite n equals c over v to be n equal the frequency of the light times its wavelength in the vacuum divided by the frequency of light times its wavelength in the medium. Now when the light enters a new medium, it's the wavelength and speed that change, but the frequency is invariant. So the next step is going to be to cancel out f. In this slide, I've canceled out f, and so in the third line I have n equals lambda vacuum divided by lambda medium. And in the fourth line, I just rearrange that relationship to solve for the wavelength of light in the medium. So I have lambda medium equals lambda sub vacuum divided by n. So now we have an expression for the wavelength of light in a medium of index of refraction n. And now we're going to marry that to the given information, because we're told that the oil has a thickness of 1/4 of the wavelength of red light in the oil. Here's a diagram of the visible light spectrum. For humans, it runs from around 400 nanometers to around 750 nanometers. So what I'm going to do is just pick a convenient wavelength for red light of 700 nanometers and apply that to our analysis of the film. We have our expression, the wavelength of light in the oil is equal to the wavelength of light in vacuum divided by n, the index of refraction of the oil. So I'm going to take the wavelength of red light I picked, 700 nanometers, and divide it by 1.50, the index of the oil, and that gives us a value of 466 nanometers. That's the wavelength of red light in the oil. And since we're told that the thickness of the oil layer is 1/4 of the wavelength of red light in oil, I'm going to take 466 and divide it by 4 and get 117 nanometers. That's the thickness of the oil. So now let's tie this all together. We have incident light coming into an air-oil boundary. That light, when it reflects off, will undergo a 180-degree phase change because the index of refraction of the oil is larger than that of air. Some of the light will refract through the oil and reflect off of the oil-water boundary, and then re-emerge into the air later. When it reflects off the oil-water boundary, it won't undergo a phase change because the index of refraction of water is less than that of oil. Since the oil is 1/4 wavelength thick, then the light that refracts into the oil layer and reflects off the oil-water boundary travels 1/2 of a wavelength more than the light that just reflected off the air-oil boundary. Therefore, the total path length difference between these two reflected rays is 1/2 a wavelength from the phase change and 1/2 a wavelength from the path length difference. So, red light reflected from the top surface interferes constructively with red light from the bottom surface because of this 1 wavelength phase change. Therefore, the film looks red. Light of other colors will experience some degree of destructive interference. So now that we've done one situation, you may want to check Facebook before we do the second situation. Here's a new situation for your meditation. We have white light and air incident on a coating of some material of index 1.38, and the coating is on top of a glass lens of index of refraction 1.52. We're told that the thickness of the coating is 1/4 of the wavelength of green light in the coating material. So here are two tasks. First is to determine what the observer will see, and the second is to get an estimate of the thickness of the coating. Do stop the video and think about this. Just watching the video does not make you into a physics ninja. Here's a solution. This time, since the index of refraction of the glass is larger than that of the coating, light reflected from both the top and bottom surfaces undergoes a 180-degree phase change. So this is equivalent to shifting both waves by 1/2 a wavelength. Then we need to consider the path length. Because the thickness of the coating is 1/4 of the wavelength of green light in the coating material, the wave that goes into the coating and reflects off the coating glass surface travels an extra distance of 1/2 of the wavelength of green light. So therefore, the light that reflects off the top of the coating and the light reflected off the bottom of the coating is shifted by 1/2 a wavelength. This means that green light will interfere destructively as it reflects off of the coating, and light of, say, red and purple will not interfere destructively so much, so the coating will appear reddish or purple. As for the thickness of the coating, here's our spectrum again, and let's assume that the green light we're talking about has a wavelength of, say, 525 nanometers. So our calculation for the thickness starts again with our relationship lambda in the coating equal to the lambda in the vacuum divided by n. And that's 525 divided by 1.38, the index of the coating. That gives us a lambda of green light in the medium of 380. And so therefore the thickness, which was given as 1/4 of that wavelength, is about 95 nanometers. This is a good time to check Facebook again. You might have missed something before we do our third situation. With our third situation, here is a phenomenon called interference from an air wedge. Here you have two plates of glass, and they're separated by a very thin sheet of paper. Drawing here is not to scale. What you observe is a set of interference fringes, that is, constructive and destructive interference lines along the length of the glass. Here's a problem from Cutnell and Johnson's Physics 3rd edition. Problem is, assuming that green light of wavelength 552 nanometers in a vacuum strikes the glass plates nearly perpendicularly, determine the number of bright fringes that occur between the place where the plates touch and the edge of the sheet of paper, and the thickness of that is 4.1 times 10 to the minus 5th meters. In other words, the problem is about finding the number of constructive interference lines that will occur, or that will be observed in this plate. Here's a diagram that might help you visualize the situation. Rays 1 and 2 are the ones that are going to interfere with each other. First thing we need to do is consider the impact of phase changes upon reflection. Ray 1 doesn't experience a phase change because the air, that is the second medium, has a lower index of refraction of the glass where the ray is coming from. But Ray 2 does, because the air that it's in has a lower index than the second glass plate below it. So the next thing we need to think about is the path length difference between Rays 1 and Ray 2. Here's a figure that might help you visualize that. Because the air wedge is sort of triangularly shaped, the difference in path length will change as you move from left to right across the wedge. So some places you'll get destructive interference, in other places you'll get constructive interference. The point of the question is to figure out how many areas of constructive interference there are. This is a thorny question, so why don't you pause the video for a minute to think about what a mathematical expression should look like that describes constructive interference. Here is such an expression. Remember that the phase changes upon reflection already give us a half wavelength phase shift, so in order for constructive interference to occur, the path length difference needs to supply the other half wavelength. So in this expression we have 2t. T is the thickness of the air wedge, and 2t is the path length that reflected ray 2 will travel in and out of the air wedge. On the right, we have an expression that involves a variable m called the order number. When m is equal to 0, that is the condition for the first band of constructive interference that occurs. In that case, the path length difference 2t is equal to 1/2 of lambda, and that, combined with the 1/2 lambda that occurred because of the phase shift upon reflection, is enough for constructive interference to occur. The next band of constructive interference occurs when the path length isn't 1/2 of lambda, but 3/2 of lambda. So in that case, the total path length difference between Ray 1 and Ray 2 is 2 full wavelengths. And constructive interference will recur whenever the path length 2t is some multiple of 1/2 lambda. So you're going to get constructive interference when m is equal to 0, so that the path length difference is 1/2 lambda, when m is equal to 1, so that the path length difference is 3/2 lambda, when m is equal to 2, when path length difference is 5/2 lambda, and so forth. So using this expression, we can actually calculate the number of m's we need. Since we know that the thickness of the air wedge at its thickest point is the same as the width of the paper, we can use that as t. And we're also given the wavelength of green light, and we're going to convert it to meters, 5.52 times 10 to the 9th. And we get a value of m of 148. But this is not our answer, because the first band of constructive interference occurred when m was equal to 0. The total number of bright bands we're going to see is actually 149. Thanks for watching, and here is a little public service announcement.